I've got plenty more.
Yep, somebody's already singing it. See, I'm telling you, I've been singing it for 4 days. I can't help it. It's just very catchy. When we were in high school, the marching band was like better than the football team. The football team was crappy, but our marching band like always had all the state championships and stuff. They were really, really good. But they used to, any Friday we had a home game, they would come through the halls, the marching band, just the drum line. And they would come through the halls in a row and they'd be like all drumming and they're coming through the halls. And they were so loud because it's like off the walls. But they were your standard, even if you're as cool as Pharrell Williams, they were still your standard band nerds because they would come, you would be trying to get to your locker, right? And you can't because the marching band's moving by. And if you tried to squeeze in between two of them to get to your locker, they'd scream at you, "Don't break our ranks!" And you're like, "I'm just trying to get in my locker. I'm gonna be late for class." But they were fun. They were fun. So anyway, interesting. It was a fun weekend. All right, so we are going to do covalent bonds mostly today, and then you have a test, and then today is lesson 9, which means it's the last lesson of the quarter. So you will be getting, after you finish your test, you will be getting your progress reports. Hooray, hooray. Oh, look at y'all. Oh, yeah. So somebody want to define a chemical bond for me. Who wants to go there? Anybody? 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 I'll do it myself then. A chemical bond is the attractive force that holds atoms or ions together. What's the difference between an atom and an ion? Hidden.
Ions have more.
Nope. Whoop, that's isotope. Try it again. Hey, more or less electrons. There you go, right? More or less electrons than the standard atom does. Yes, the parent atom. Oh, when are they what? I haven't done them yet. I'm gonna do them later. For that, I'll separate. You know, I try and balance them out as best I can. I try to scramble people up. All right, your 3 main types of chemical bonds. So first you have ionic bonds. And somebody want to define that for me? What's an ionic bond? All right, Lucas. Right, so it's going to be a bond between two, hang on, it's going later. Oh, shoot, okay, yeah, but bond between 2 atoms. I forgot there wasn't a thing there. And then you have, then you have covalent, and then you have, your covalent is broken down to polar and nonpolar, and then you have metallic bonds. All right, so yes, this should be a 2. I caught it, I just didn't say it. Anybody want to guess what this one is? It's not meth. It's not ecstasy, but you're close.
Isn't it also called ecstasy?
No, it's a different. So methylene dioxymethylamphetamine is also known as MDMA, Molly. If you've heard of Molly.
Yeah. And it's also known as ecstasy.
Yeah, oh yeah, ecstasy. But ecstasy, I think technically has something else in it besides just this. But yeah, I'll give it to you. Yeah. So Molly, most of the time, if it's MDMA, they'll straight call it Molly on the street. So it is a potent empathogen antactogen with stimulant and minor psychedelic properties. MDMA is part of the amphetamine family, and it's mainly used recreationally, but this is one of those ones that some people use it for themselves and some people use it on other people. If you've ever heard of a category called date rape drugs, this is usually like one of the top ones. Rohypnol would be another. Yes, this is a different one. MDMA is one too. So, but this is something, this has got covalent bonds. All right. So ionic bonding, here we go. What is a compound composed of ions bound together by electrostatic attraction? All right, Yusuf. That's an ionic compound, all right? What is a collection of atoms corresponding to an ionic compound's formula, such as the molar mass of the compound is the same as 1 mole of the formula units? Does anyone have this one? That's our formula unit. Basically, remember like NaCl is a formula unit. It's a compound, it's a formula unit. It's not a molecule. Molecules have covalent bonds. KCl. It's another one that you used a couple weeks ago, potassium chloride in lab, right? That's another formula unit. So what is an ion made of 2 or more atoms? Do we know what that is? All right, Caitlin. No, Jordan.
Polyatomic.
There you go, polyatomic ion. So sometimes ions are made of 2 or more atoms, and those are polyatomic ions. So metal and non-metal make an ionic compound, sorry, a formula unit is formed from a metal and a non-metal. Remember, sodium chloride, metal, non-metal. You guys good in the back? And then in an ionic compound, you have complete transfer of electrons, stealing and donating. So let's think about it again. Sodium chloride. He's got 7 in his valence. He's got 1 in his valence. Which one is going to donate an electron? Yeah, the sodium, right? Always going to be the metal that donates, and the non-metal is going to steal it. That's the idea. All right. Where are you? There you are. Accepting it happily. And they form ions, and they are solids at room temperature. They have high melting, high boiling points. You saw that today. Strong bonds. They're brittle. They're non-conductive, but when they're in liquid solution, they're excellent conductors. Remember, these are all our ionic compound things. And they have full ionic charges. We're going to get to balancing ionic equations in a couple weeks, and you can see how all the charges work, and it's pretty crazy. So ionic bonding is a force that attracts electrons from one atom to another, which transforms a neutral atom into an ion. An ionic compound is a 3-dimensional network of positive and negative ions mutually attracted to one another. And remember, they form a crystal lattice like this, right? Ionic compounds tend to be harder and more brittle and to have higher boiling points than materials containing only covalently bonded atoms. Did you see that today? You had your covalently bonded sucrose, low melting, low boiling point. Also, note that, hang on. Oh, stop going. Note that this right here, remember that another characteristic of ionic compounds is that they tend to be brittle when a force is applied, they're brittle, right? Like if you you can't bend salt, right? You can't bend it. It's gonna shatter into pieces. All right, we got a bunch of definitions here. Let's make sure we know all these. So what do you call a group of atoms that are held together by chemical forces? A molecule is the smallest unit of matter that can exist by itself and retain all of the substance's chemical properties. Do you know, Xander? There you go. Okay, so a molecule is the smallest unit that can retain all of its properties. Now remember that a molecule can contain different atoms covalently bonded or multiples of the same atom. What's an example of a molecule where you have multiples of the same atom? Jordan.
2 oxygen.
Yep, oxygen's never by himself. It's always O2. You got another one? Well, that's got 2 different atoms, right? You got H and O. Guys in the back, I don't want to scream at y'all, so let's not yell. Okay. Yeah, don't make me yell. So what is a chemical compound whose simplest units are molecules? Do you know?
An element?
Not an element. The simplest units are molecules. So these are the molecular compounds as opposed to the ionic compounds. If your simplest unit is a molecule, you are a molecular compound. Whereas if your simplest unit is ionically bonded, you have an ionic compound. So what is a combination of chemical symbols and numbers that represent a substance? This would be like C12H11O22. What is that? Yeah.
Formula unit?
So it's a molecular formula, real close. So formula unit is used for ions. Molecular formula is used for covalently bonded molecular compounds. You can call both of them a formula in general. You can say the formula for sodium chloride is NaCl, but you can't call that a molecule or a molecular formula. It's a formula unit. C12H11O22 is a molecule or a molecular compound or a molecular formula, right? Because they're not ionically bonded, they're covalently bonded. Does everybody understand the difference between what's a molecule and what's not a molecule? Is O2 a molecule?
Yeah.
Yeah. Is H2O a molecule?
Yeah.
Is C6H12O6 a molecule?
Yeah.
Yes. Is NaCl a molecule? No, it's ionically bonded. It's a formula unit. It's a compound, an ionic compound. How about KCl? No, right? Again, it's not a molecule. It's a formula unit. It's a ionic compound. So what's an electron configuration notation in which only the valence electrons of an atom of a particular element are shown? And it's indicated by dots going around the symbol. Caden. Lewis dot. So you can call these Lewis dot. You can also call them, what do they call them? Atomic dot. There's another way to call it too, but Lewis dot is probably the best known because, you know, Lewis said, oh, I have an idea. So here's your purpose for those. You can place the little dots and you can actually see how those valence electrons behave. And you can see how the valence electrons of one atom are going to behave when they come in contact with the other atom, because you can see where the spaces are in that valence, which is the point. So what is a structural formula in which electrons are represented by dots, dot pairs, or dashes between atomic symbols that represent pairs? Colin. There you go. So there's your Lewis structure. So Lewis has dots and he has a structure. And then when you see a Lewis structure, it has like little lines here and sometimes like little arrow things, but it gives you an idea of how it's bonded, and it also gives you an idea of the types of bonds involved. There's a lot going on in those. So a formula that indicates the location of atoms, groups, or ions relative to one another in a molecule and indicates the number and location of chemical bonds. Does anybody know this one? All right, so this one is your structural formula. So now we've got different kinds of formulas, right? We have a chemical formula. We have a molecular formula. We have a Lewis dot structure, a structural formula. We have electron dot notation. There are all kinds of ways to model what's going on in a compound. All of these are just different ways of modeling it. Sometimes it's writing it out, H2O. Okay, that's in a way you've modeled what's going on there. You have 2 hydrogen, 1 oxygen, H2O. And then you can also draw it out with the little dots around it. Lots of ways to do it. A covalent bond in which 2 atoms share 1 pair of electrons. All right, Xander. Single bond, 1 pair. Single bond is 1 pair. Oh, you're thumping over my mother's head. She's down there trying to watch her TV, loving her retirement. That's your single bond, 1 pair, 1 pair. So how many electrons? 1 pair is 2, thank you. All right, a bond in which atoms share more than 1 pair, such as a double bond or a triple bond. What do we call those? Everybody went, oh no, that's a multiple bond. So there are double bonds which share how many pairs?
2.
Triple bonds share how many pairs? 3. And they are types of multiple bonds. So you have single bonds, multiple bonds. Multiple bonds is broken down into single, double, right? I mean, triple, double, sorry. The bonding in molecules or ions that cannot be correctly represented by a single Lewis dot structure. Okay, this is resonance. All right, so we talked about resonance in physical science. Who remembers what that is? Do you remember?
How the waves move.
Has to do with how waves move. Drew?
Vibration in which molecules need to move in order to break apart.
Yeah, that's kind of where it's coming in. Yeah, but do you remember resonance from physical science? Like what was, yeah.
It's, well, like the resonant frequency is the frequency you can use. It's like when you watch the bridge, the bridge when, it's why soldiers don't march when going over bridges, because if they march at the correct frequency, the bridge will collapse.
Right.
And there was a windstorm
Mm-hmm.
that hit there was a bridge and
Mhm.
it got flexible material.
The Common Arrows Bridge.
And,
Yep.
Yeah, the bridge would.
It just started swinging like mad. Yep. Exactly. Yeah, and that's what happens with resonant frequency. If you meet the natural vibration of something, and basically you can amplify it, and then it can cause problems. This is also how like people break glass by singing particular notes and pitches and things like that. It's the same idea. It's also if you have two tuning forks side by side and you flick one, the other will sympathetically vibrate. So you do have that going on down at the level of atoms and compounds, down at the molecular level, which is kind of crazy, but it does. So a metal and a non-metal make what? What kind of compound? Caitlin? Not a covalent. Metal and a non-metal make Colin. Ionic compound, right? And then you've got sharing electrons, and this happens in what type of bonds?
You have non-metal and non-metal.
Oh, yes. I meant to say that actually. It's not a brownie point. I was meant to say to follow the thought with a metal and a non-metal make an ionic compound. A non-metal and a non-metal make a covalent. Thank you. My brain died in the middle of that. Yes. So yes, a non-metal and a non-metal will make your covalent compounds. Yes. Oh, sharing. Yes. What's sharing? Sharing, ions don't share. They steal and donate. Covalent compounds share. They form molecules, not formula units. They are solid, liquid, or gas at room temperature. What are ionic compounds at room temperature? Do you know? They're solids. Yeah. What type of solid are they? Do you remember? Not metals. Ionic compounds. What are they? They're what type of a solid? How do they look when they're James? Crystalline. Yeah, they're crystalline solids typically, like salts. Think about salts. Whenever you think about ionic compounds, think about salt and try to think about what are the characteristics of this salt, right? Okay. They have covalently bonded molecules have low melting and low boiling points, which you saw today with the sugar, right? So when you're ever trying to compare, if you're ever trying to compare ionic compounds to covalent compounds and what are their characteristics, I want you to think back to today's lab with the salt and the sugar. Your salt's your ionic compound. What could you not do with it? I couldn't melt it at my temperature. I couldn't boil it. It was a crystalline solid, but not all covalent compounds are going to be like that. So that one for the sugar doesn't apply, but can you stretch ionic compounds? Can you stretch them? No, they're real brittle, right? They're real brittle. They'll shatter, but can you stretch sugar? Because covalent things there tends to be some flexibility in the bonds. So their bonds are weak, which is why they're flexible.
Yeah.
And they can be brittle, but they're not necessarily brittle. They're not always brittle. And they they're not always, tend to be soluble in water. Yes.
How does the sucrose melt in the microwave if there's no water molecules that vibrate or heat up?
There probably is some level of water in it. It's probably not, that's a great question. It's probably not ever going to be 100% water-free because you've got water in the environment. So there's going to be some water that attaches itself to them just electrostatically, just because it exists. But that's a great question. Because microwaves heat by changing the polarity of a water molecule back and forth, and you get friction, right? So they're poor conductors. Polar. Okay. If the covalent bond is polar, it means that the electrons that are being shared are not being shared equally. So this happens between two different nonmetals, and what happens is one tends to pull more than the other. And that usually has to do with how much energy is at that particular valence shell. Okay. And then nonpolar is when they're being shared exactly equally. One's not pulling too harder than the other. And it's often between two identical nonmetals. Identical because one is not going to have more energy in the valence than the other because they're identical. And you get no charges going on. All right, so covalent bonding occurs when atoms do what? One or more pairs of electrons. When they do what with them? Caitlin.
They share electrons.
They share, when they share, right. When they share one or more pairs of electrons. So covalent bonding occurs when atoms share one or more pairs of electrons. Okay, remember that with ionic bonding, it's not sharing, right? One's kind of donating or giving it up, the other is stealing. So yes, but in covalent bonding, it's being shared. So what do you call a covalent bond? When the electrons are equally attracted to both atoms? We just said this. What do you call it? Okay, Xander. Yep, those are the nonpolar ones. And then what do you call a covalent bond that occurs when electrons are shared by two atoms, but it's held more closely to one atom? Jordan. Those are the polar ones. Okay. Atoms in molecules are joined by what kind of bonds? Again, if it's a molecule, what kind of bond is it? Yusuf. Yep, if it's a molecule, it's a covalent bond. In covalent bond, two atoms share one or more pairs of electrons. Guys. So what states that many chemical compounds tend to form bonds so that each atom shares or has 8 electrons in its highest occupied energy level? We talked about this a couple weeks ago. Why is that? What is it? All right, Xander. Octet rule. Remember octet, 8. You want 8. How many do these guys have in their valence? 8. How many do these guys have in their valence? 7. How many more do they want?
1.
They want 1. How about these guys over here? How many do they have?
1.
They have 1. But what do they really want?
0.
They really want 8. But it's harder to get 7 more than it is to give up 1. And that's where your ionic bonding occurs. Same thing is going on in here, but we're still trying to get 8. So if we're trying to get 8, you can have combinations of 3 and 5. You can have 2 and 6, for example. That's what you're trying to get at, is 8. Bonding with many molecules and ions can be indicated by what kind of a structure? We talked about it a minute ago, Caitlin. Yeah, Lewis dot is what we're talking about. But yeah, you're fine. Molecules or ions that cannot be correctly represented by a Lewis dot structure are represented by atoms, which is, we'll talk about that later. We won't even worry about it too much, really. So what's the ability of a substance to be hammered or beaten into a sheet? Yeah. Not ductility. Liam? Malleability. Okay. Malleability is the ability to be hammered or beaten into a sheet. So we're talking about metallic bonding now, all right? Metals, as you remember, can be hammered or beaten into a sheet. And the reason they can be hammered or beaten into a sheet is because of the metallic bonding, which is the bonding between all of the various atoms within a metal. Okay? So you can have a sheet of gold and you can hammer it into a sheet. The Gold Dome in Atlanta, or Capitol Building for the state of Georgia, they've got scaffolding up right now, and I don't know why. But if you've ever looked at it, you ever see it? It's gold. It's actual gold. It's Dahlonega gold that they've hammered down into super, super thin little sheet. Yeah, it's gold.
Solid gold.
Is what? No, it's got a gold foil on it.
Are you arguing with the teacher?
Feel free, but you're wrong on that. It's not solid. It's got lots of structure underneath of it. All right, so the ability of a substance to be hammered thin or drawn into a wire. What's drawn into a wire, Colin? That's ductility. All right. Can you take salt and draw it into a wire? No, because it's an ionic compound, so it's brittle. If you apply force to it, it's going to break apart. But metallic bonds, nice and stretchy, you can pull it into a wire. And what do you call something that is conductive for both thermal and electrical activity? It has good, what, Jordan?
Conductivity.
Yeah, conductivity, basically. All right, so your metallic bonding is what's responsible for these properties of metals: ductility, malleability, thermal conductivity, electrical conductivity. They're all because of the way the bonds work. So we're going to talk about why that is. All right, so a metallic bond is formed by the attraction between positively charged metal, what? Ion. Right, a positively charged metal ion and the electrons around them. Okay, so if you have a sheet of aluminum, like aluminum foil, all right, and it's been hammered out nice and thin, can you run electricity through it? You can.
Yes.
You can. Some experiments you can use little bits of foil. Yeah, aluminum foil. So it's not the world's best, but it works. Let's say, let's use copper as an example. Can you run electricity through copper?
Yeah.
Okay, say you got a copper sheet All right, like last year in one of our labs, we did the whole telephone thing where we squeezed the little cups with the carbon granules in them. And inside were these copper plates. Do you remember? And as the plates got closer together, suddenly like the light came on. So the reason that works is because you have all of these little copper ions and they're all bonded together. Okay, they're all bonded together in this structure. And then around, excuse me, around them, you have all of their electrons. And their electrons, their valence electrons are whizzing around. Now, most of the time, a valence electron is going to stay with its atom. But in a metal, they move between all the atoms. So you have electrons that are just constantly moving. They call it an electron sea. So because of that, that's where your thermal and electrical conductivity come in. That's why metals are so good at conducting electricity, because those electrons are free to move. They're just free to move everywhere. So the electron sea is formed in metallic bonding, and it gives metals their properties of electrical and thermal conductivity, but also malleability, ductility, and luster. What causes the luster? Do we know? Why are they shiny?
The light, the photon reflecting off the.
Yeah, so if you take something that's a shiny metal, this little Lennox thing that my mother-in-law gave me has gold on its little toes. It's probably real gold because it's Lennox, you know. But it's shiny, right? It has luster. So that means that the valence electrons in that gold are the valence electrons in the gold are actually absorbing the light and re-emitting it, which is why they're metallic. This is why they have luster. So other types of bonds. All right, let's see. What's an intermolecular force occurring when hydrogen atom is bonded to a highly electronegative atom of a molecule that is attracted to two unshared atoms? Do anybody know this one? Okay, this is hydrogen bonding. Okay, this happens between water molecules, hydrogen bonding. And this is super important because without hydrogen bonding, water as a body would not have the properties it has now. The reason water has surface tension is because of the hydrogen bonds between water molecules. So it's essential that we have those types of bonds. Yeah, well, it also has to do, it also affects water's properties in such a way, like for most things, when you cool a substance, what happens to its volume as a general rule?
It expands.
When you cool it,
Oh, no, it shrinks.
it shrinks, right? When you cool, most things when you cool them, they shrink to some degree. Water will do that to a certain point, and then what happens when it freezes?
It expands.
It expands, okay, and it's expanding because of the way those hydrogen bonds are set within the water. They have to spread out, and then it forms that crystalline structure that we know as ice. If water didn't do that, then what we would have is ponds, and this is because ice is less dense than water, because when it locks into that crystalline structure, when it freezes, it becomes less dense, right? It floats. If you put ice in your glass, it floats. If ice didn't have that characteristic, ponds and lakes in the winter, when they freeze, they would freeze all of it, and you wouldn't get the ice on top. So what would happen to all the things living in the water? They don't freeze to death, right? So the fact that the ice goes up to the top, just that, like we couldn't have life on Earth without the hydrogen bonds doing what they do.
If your ice sinks and there's normally something in the drink, and you shouldn't drink it.
There you go. It's a good tip. Have you ever seen this is a good trick too. If you're like leaving your house because you're evacuating because of a storm, one thing that they'll tell you to do is like freeze a cup, like a plastic cup of water, and then put a put a penny on top of the ice and leave. And when you come back, if you open your fridge and the freezer and that penny's still on top, you didn't lose power. Because if you lost power and the ice started to melt, your penny would sink. And you would know that all of the food in your fridge and your freezer is no longer safe. You wouldn't necessarily know that, because you could have steaks in there and you could have no power for 3 days and your steaks could spoil and then freeze again and you wouldn't know, right? So that's a good trick. So we have ionic bonds, covalent bonds, metallic bonds, and James Bond. There you go. He's right there. James Bond. Yeah, there you go. So what's the energy required to break the bonds in one molecule of a chemical compound? What do we call this energy? Anybody know? She's looking. Do you know, Caitlin?
Bond energy.
Yeah, very good. So the bond energy is the energy required to break the bonds in one molecule of a chemical compound. All right, what's the energy associated with constructing a crystal lattice to the energy of all constituent atoms separate by infinite distances? That's a fun thing. How about just the energy associated with constructing a crystal lattice? What is that, Jordan? Lattice energy. Okay, so it takes energy both to break it and to form it. And what's a molecule or a part of a molecule that contains both positive and negatively charged regions? Do we know this one? Okay, so this is a dipole. All right, sorry, that was too fast for you. So some molecules have positively charged regions, negatively charged regions, and they're called dipoles. All right. Now, one way we take advantage of poles in general is by the use of surfactants. Does anybody know what a surfactant is? No? Nobody knows? Okay, so water molecules are polar, okay? And so are molecules of fat, for example. And this is why water and oil don't mix. If you put water in your measuring cup with your oil, it's going to stay separate, right? And that's because they're repelling each other. But a surfactant has the ability to bond to both. So it can bond with the fat and then it can bond with the water. So your dish soap that you use at home is a surfactant. And what it's doing is it'll take that oil and water, it'll grab both of them at the same time, which allows you to kind of swish it around and get the grease off of your dishes. That's how it's working, right? Surfactants biologically speaking, your lungs produce surfactant. And surfactants tend to be like kind of soapy and slippery. And your lungs produce this so that when you exhale, all of those little tissues, those spongy tissues in your lungs don't just stick together and not open again. Because they're sticky, right? They're wet. What if they stuck together and didn't open again, right? But surfactant production doesn't happen until like within the last couple weeks of gestation, because you don't really need it when you're breathing amniotic fluid in and out, right? You don't need it. But premature babies are often born before their body is producing enough surfactant to keep their lungs open when they exhale. So they can treat them so that they can produce it faster or sooner. But also, if anybody ever seen a video of a preemie on a ventilator? If you've seen a video of an adult on a ventilator, it's right? The little babies are, it's constant, like their lungs are going like this. Their little chests are just vibrating like crazy because they're trying not to give it time to seal up. It's just constant in and out real fast, like a butterfly almost, like fluttering. It's pretty weird to look at, but that's why they do it that way. All right, so now we have VSEPR theory and molecular shape. Some people are going to say Vesper theory. I've heard people use the term, but it can confuse you because you don't know what order these are going in, right? Like if you say Vesper and you spell Vesper the way Vesper is spelled, that's not going to help you. So VSEPR theory and molecular shape. So this is the theory that predicts some molecular shapes based on the idea that pairs of valence electrons surrounding each atom repel each other. So when we talked about kind of like Lewis structure, it's this sort of idea. So this is yet another way to represent or diagram how a molecule functions. So basically, there are patterns, okay? And I'm not going to expect you to know all these patterns, but I want you to know that they do exist. These, I'll tell you right now, these are the easy ones, as crazy as this looks. If you go into organic chemistry, it's a whole nother level of learning to draw hexagons really well, because it's a lot of drawing hexagons, because there's benzene rings and all this business, and they're very common, so everything has a little hexagon in it. Remember back to that MDMA molecule? The drawing had a little hexagon in it? Yeah. So different types of shapes are linear, like that, right? Trigonal, planar, bent, linear, tetrahedral, trigonal pyramids. More of these can be bent or linear. So you can see, like, if you look here, you can tell this is supposed to be a 3D image, right? It's supposed to show you that this goes up, this goes to the side, that goes back, this comes forward. Gives you an idea of what you're looking at. Oh, I always do that. All right, so this is a memorizing tip. Should you care to memorize them? I'm not going to require you to, but should you care to? This explains it.
Here we talk about chemical bonding. In that, we take VSEPR theory here. And I know you're not able to learn some shapes of the molecules if you're given about the lone pairs and the bond pairs. But I now have a very interesting way that you can learn them very easily. Yes, you will not forget them. See, what you have to do is make a table like this: 21, 22, 31, 32, 41, 42, and 51. Now, separate them. These are bond pairs, these are lone pairs, and here we have the shapes. Bent, bent, trigonal pyramidal, T-shape, seesaw, square planar, and square pyramidal. If you learn about them the way I want you to, then you will not forget it. Yes. Look, B comes before everything alphabetically, but you'll say T comes after S, but you just remember beats. Just B everyone with an S and last. Okay. Now see, for remembering which one comes before in T pyramidal and T shape, go alphabetically. Here we have the P and here is X. Which comes before? Simply P. And in these three, you can learn it like at 41 Street, she saw me.
Seesaw me. I love that one.
We had 42 square planar and 51 square pyramidal. And if you look which one comes before in these two, then you can see here we have L is alphabetically before Y. These are, very good way.
It's actually helpful. If you weren't required to memorize them, it's actually a really good tip.
Band, T pyramidal, T shape, see, saw me at 41 Street, we made 42.
41 seesaw me, 21 street seesaw me.
Being like,
That one makes me laugh. Seesaw me.
don't just skip it. Don't know.
Do not just skip it. Do not just skip it, he says. Memorize it. Do not. Okay. So now we're going to talk about ionic charge for transition metals. So what we have talked about for the most part in the last couple of classes are the alkali metals, the alkali earth metals. We haven't really talked about all these transition metals. Okay. So if they can form bonds, then some of them are going to be involved in ionic bonding. So how do we get the charges? All right, so this is a good one. This so tired. Can we please just have this election? Yep.
In this video, we'll talk about how to find the ionic charge for transition metals. So when we find ionic charge, to look for ionic charge, we often think of this pattern on the periodic table. Group 1 forms 1 plus ions, group 2, 2 plus, and we skip the transition metals. That's what we're interested in this video, but we skip them and we go 3 plus, 4 plus or minus, and 3 minus, 2 minus, 1 minus 0. And that's very useful to understand the general trend for ionic charge on the periodic table. It's a bit of an oversimplification though. If we looked at a more detailed periodic table, we'd see that we still have group 1, they're all 1 plus, 2, 2 plus. So here are the transition metals. We have these post-transition metals, some of these down here like lead. So this is a little more detailed, and you'll note that there's really no 4 plus or 4 minus on this table. So here we have 3 transition metals though that always have the same ionic charge. Silver, 1 plus, and then zinc and cadmium, they're always 2 plus. But for the rest of them, some of these transition metals down here, we really don't know what the ionic charge is. To find it, we'll look and see what it's bonded to. So these are all positive. We'll see what they bond to here, and then we can work backwards to determine the ionic charge. So let's try that, see how it looks. Let's try copper oxide. So copper transition metals right around here. We don't know its charge, but oxygen, we know that oxygen right here has a 2- ionic charge. And this copper oxide right now, it's neutral. There's no plus or minus out here. So all the charges, they add up to 0. The net charge is 0. Oxygen, 2-. That means for them all to add up to 0, the copper has to be 2+, and that's its ionic charge. We would say for the name, copper 2 oxide. And the 2 would be a Roman numeral in parentheses after the word copper. So copper 2 oxide here. Let's try another one, maybe a little more complicated. How about Fe2O3? This is a component of rust. So we don't know what iron is, it's a transition metal, but we do know again that oxygen, that has that 2- charge. So we'll put our 2- charge up here. And we know that all the charges on the Fe2O3 compound, they have to add up to 0. So 3 times 2-, that's 6-. So this part of the compound is 6-. So the question is, to get 6+, what is the charge on the iron? 2 times something will give us 6+. So 2 times 3+, that'll give us 6+.
Pay attention to this, because you're gonna be writing net ionic
Zero.
equations
So the
soon, so this matters.
on the iron is 3+. We call this iron 3 oxide. And note that this 3+, there's 2 iron atoms, so each one is 3+. Now you try one. How about CuCl2?
I will pause it for a second. See if you guys can figure that out for a minute. CuCl2. Look at the chlorine. What's the charge on chlorine? -1. How many chlorines do you have? So how many negative charges do you have there? So it's 2-. So what does the copper have to be? Okay, you're catching on.
For CuCl2, again, copper, that's a transition metal right around here. Chlorine, that's right here. It's in group 17, sometimes called 7A. All of these have the 1- ionic charge. Right, 1- up here. 2 times 1-, that's 2-. So the copper, to have this 2+, so these add up to 0, has to be 2+. Kind of imagine a 1 times 2+ gives us the 2+. Net charge is 0. The charge on copper is 2+. We call it copper 2
chloride. There you go.
Pause and try this one.
All right. See if you can figure out what the charge is and also what the name is. Okay, find your S.
S-2.
16, so it's -2 times 3. So it means it's plus. So what's the charge on the iron ion? One of them would be 3, right? 2, and there are 2 there, so yes, 6, right? So then what's it going to be called?
Iron 3
Iron 3
sulfide.
sulfide.
Ah, you guys are good.
So for Fe2S3, it's pretty much the same as Fe2O3 because these are in the same group. Overall, neutral compound. So we look up oxygen right there, 2-, 3 times 2-, so we have 6-. This has to be 6+. 2 times 3+, that'll give us 6+. Net charge is 0. Iron 3 sulfide. We'll wrap up with one more. ZnCl2. So again, neutral compound, all the charges add up to 0.
And give it a try. It's 2. Yeah? You think you know it? You think you know it, Gabe? You got a hand up. You know, he's like, nah, never mind. I take it back. Do you know it, Jordan? Okay. Let's see how we do.
Fluorine, that's right here, that has that 1 minus. We have 2 of them, so 2 minus. The zinc has to be 2 plus. But we also know zinc is an exception for the transition metals. It's always 2 plus. So we could have known that without figuring out the chlorine. If we name this compound, because zinc is always 2 plus, we can just call it zinc chloride. We don't have to call it zinc 2 chloride.
My man.
Zinc chloride. This is Dr. B with the ionic charges.
Thanks,
for-
Dr. B. All right, now we got one more. That's naming some ionic compounds. Now we got to name some covalent compounds. Okay, so this is gonna be a little. What out are we gonna get? Oh, Wix! Yay! I'll take Wix.
Unlimited creation.
I like Wix. All right, here we go. It's just not politics.
Science, this video, I'd like to talk about writing covalent compound formulas. Covalent compounds are composed of 2 metals. You can find the nonmetals on the right side of the periodic table. Covalent compound formulas use prefixes. The prefixes go like this. Mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona 9, and deca 10. It will help you if you memorize these. Let's get started with a couple of formulas, and I'll go through some of the rules. Up first is CO. Rule number 1, with the first element, if it does not have more than 1, or in other words, if it's just 1, you just say the element. You don't say monocarbon. And then for the second one, you do add the prefix. So this will be carbon monoxide. Up next is N2O. Now we have 2 nitrogens, so we will use a prefix of di. So it will be dinitrogen monoxide, because you only have 1 oxygen. Also notice that instead of all of oxygen for the second term, you use IDE. Next, you have N2O3. So let's put all the rules together. You have dinitrogen because you have 2 nitrogens, and then you have 3 oxygens, so it will be tri, and then you add the IDE, so it would be trioxide, dinitrogen trioxide. Now let's work it the other way. Up first, we have SO2. That will be sulfur, because you only have 1 of those, and it's the element name, so it'll be sulfur. Then you have 2 oxygens, it'll be dioxide. Next,
What's that one?
Phosphorus, triphosphorus.
Phosphorus is 1. We only have 1. What do we have there?
Phosphorus, hydrogen.
Tri-high. Oh, okay.
PH3,
Yeah.
and that will be
There we go.
phosphorus
Trihydride.
hydride.
There you go.
And finally, you have CH4.
Oh. Carbon.
Carbon.
Actually, I forgot. Carbon tetrahydride. whatever.
Carbon tetrahydride. Okay. Okay. Yep.
Carbon tetrahydride.
Oh, so good.
It's also methane.
Naming,
Common name methane. There you go.
watching, and
All right. So. Yeah. All right. Let's try some then. So, what's this here? H2O2. What's its chemical name gonna be? Do you know, Jordan? So this one's trickier. This one is hydrogen peroxide. Why? I honestly, this is one of those ones where it's kind of like a weird chemical name. This one, anybody want to take a guess at, okay, so hydrogen peroxide, this is hydrogen peroxide that you use, like when you say I could get peroxide on my cut, that's what it is, okay? Bleach is sodium perborate. Anybody want to give sodium perborate a shot? Oh, PJ wants to try it. Go ahead, girl. What you got?
S2B2.
S2B2. Close. So sodium Na. There you go. There's your B for boron. BO. When you see an O with something, like something with an O, like BO is borate, SO is sulfate. That's where the 8 is coming in, right? These are tricky. Okay, borax looks like this. Na2B4O7 with, that's what the dot is, 10 waters. Anybody want to give it a shot as to what that chemical name would be? Do you want to give it a shot?
Sodium
Yeah, it's a fun one, right? Sodium tetraborate, you were right. Deca, now this right here, 10 oxygens is decahydrate. That's where that comes in. All right. Anybody ever heard of hellfire and brimstone? What is brimstone? There it is, sulfur. So the chemical name is just sulfur. Not so hard. Cream of tartar. You ever cook with cream of tartar?
Yes.
I guess you put it in meringue, a couple other things. It's potassium hydrogen tartrate. If you've ever wondered what the heck tartar is, it's coming from tartrate. I actually looked that up years ago because I was like, what is cream of tartar? What are we creaming? What are we creaming? Where are we getting this cream from? If it's cream of cow, I know what it is. But what is cream of, yeah, you know what I mean? Like cream of cow, I understand. Cream of tartar, what's a tartar? It's not, because I'm thinking it's not stuff in your teeth, clearly. So it's potassium hydrogen tartrate. You want to give it a shot? Wait, what's potassium? K. Okay, shh, in the back. K. Uh-huh. Ooh, now tartrate. So tartrate, yeah, there's an oxygen, you're right. So tartrate is actually this combination right here. It's the C4H4O6 is tartrate. This is the potassium hydrogen. This would be the tartrate, which is something completely different. Oh yeah, aren't these fun? How about this one? Epsom salt. Anybody like a good bath? I do. Okay. What you think?
I have the first,
Okay, what's the first part?
magnesium.
Yep.
Sulfate.
Yes, say it. Magnesium sulfate and then times 7 water would be what? Hang on, she's going to get this one. I know she is. So all you need is the prefix and then hydrate. So what's the prefix for 7? That 7. Yeah, you got it. Magnesium sulfate. Do it help her, Liam? She's right there. She's got it. What is it? Okay, there you go. Hepta. Sorry, I was saying septa. Hepta. Yes, right. My brain died again. My brain's died twice today, but I've been like shaking and dropping things all day, so it's not a surprise. Magnesium sulfate, heptahydrate. There you go. So that's that one you can read real easy, right? Magnesium sulfate, heptahydrate. Okay, this is a fun one. Freon. What's freon? Where do we use freon? Do you know? Anybody know where freon's used? No? Do you know? Air conditioners. Yes. You ever heard anybody, I need to get my air conditioner charged. Basically, you've run out of freon. Freon is difluoromethane. All right, we saw methane a minute ago, and he didn't tell you it was methane, but I pointed out that it was methane. So that might help if you remember. Does anybody want to check difluoromethane? Colin, you want to give it a stab?
CO2, F2, CH4.
Oh, look at this. All right. We're real close. Yes, CF2. Yep. Cl2. So the methane, I think there should be a CH4 after that. You're right. I don't know why it's not there, but I think that one was wrong. Yeah. I'll have to check it. Okay. Galena is lead 2 sulfide. Anybody want to give lead 2 sulfide a try? It's like a type of mineral. That's what we're talking about here. Do you want to give it a shot, Yusuf?
PB, PB, sulfur is sulfide, right?
Sulfur is sulfide. Yeah.
BS3,
Okay, it's just going to be PBS because your sulfur needs 2, so it's a -2, which means that their lead has to be a +2, so that's where you get your lead 2 sulfide. All right, what's graphite? Yeah, there you go. Everybody got that one. Gypsum. It's calcium sulfate dihydrate. Anybody want to give that one a shot? Jordan, you want to give it a shot?
CaSO 3 or 4,
Okay.
and then 2 H2O.
Okay. All right. Yep. CaSO4 and then 2H2O. So he got it. Very good. Hey, you got a knack for this one, Jordan. All right. Hypo. Basically, this is sodium thiosulfate. I've never heard anybody call hypo. I've never heard that used. So this just came on this random table. I don't know why. Okay, laughing gas. What's laughing gas? Do you know? Nitrogen dioxide. Okay. Anybody ever had laughing gas?
Yes.
Yes? Did you enjoy it?
It was fun.
Did you get to pick a smell, like a scent for it or no? No.
I don't think it's.
Oh, bubble gum. I remember they used to like Cole had to have it every time because he does not do well at the dentist, and every time he goes to the dentist, they find more cavities. So every time he had to have stuff done. So they would give it to him, and then they'd tell him to keep the little piece and bring it next time and pick a different flavor gas. Yeah.
I've never had any cavities.
Wow, good for you. I've had more than I can count. Shh, guys in the back. Katie.
The next one, CO.
CO, he says, calcium oxide. Very good. And how about limestone? CaCO3. What is that?
Calcium trioxide.
No, somebody said it. Somebody say it louder. Who said it? Did you say it? Calcium carbonate. Yep. Do you say? I thought somebody back there said it. All right, Andrew. Calcium carbonate. Okay. That's your limestone. All right. Let's talk about Lewis dot structure. And this is an example of Lewis dot structure using nitrogen.
For nitrogen, we have 5 valence electrons. So we can put the N in the center to represent the nitrogen with 5 dots around it. Those represent the valence electrons. Remember, valence electrons are the electrons that are involved in forming chemical bonds with other elements. That's why they're so important in chemistry. We can find the number of valence electrons using the periodic table. The group number tells us the number of valence electrons for the element. For example, hydrogen has 1 valence electron because it's in group 1, sometimes called 1A. If you look at group 2 or 2A, you'll see that those elements have 2 valence electrons. We'll skip over the transition metals since they're a bit more complicated and probably don't apply to you. We'll go to 13 or 3A, which have 3 valence electrons, then 14 or 4A. Each of those elements in group 14 or 4A have 4 valence electrons, all the way up to group 18 or 8A, which have 8 valence electrons. Nitrogen, which is in group 15 or 5A, has 5 valence electrons. So to draw the Lewis dot structure for nitrogen, we'll put the N with 5 valence electrons around it.
So when you're
So that's the
drawing
Lewis
your
dot structure for nitrogen.
yeah.
This is Dr. B.
Thank you, Dr. B.
Thanks.
When you're drawing your valence electrons, you do it in a circle. It doesn't really matter what side you start on, but you do like 1, 2, 3, 4, and then you start over again. And that's why you don't put 2 on one. You don't fill one side before another. You just go in a circle until you get them all. Yes.
I have no word for the 2 dots.
So like I said, it really doesn't matter. You can put them anywhere. You can put them on top. You can put them to the side. If you're drawing it out for the purpose of showing how one atom bonds to another, you probably want them over here on the left or on the right, depending on how you're writing it out. But it doesn't matter as long as you see the number. But this person clearly started at the top and went 1, 2, 3, 4, 5. Right, so you just keep going in circles until they're all full, then you have 8, right? So you're only doing the valence, so you're always going to have 8 or less, right? Right. Thank you. So in this case, you can see where this covalent is kicking in. Covalent bond is kicking in. So when two chlorine atoms form a covalent bond, each atom contributes one electron to a shared pair. How many valence electrons does chlorine have? 7, right? It's over here in this group, 17, 7A, right? So if they each have 7 and they share a pair, now they each have 8 when they're bonded. Does that make sense? So if this, of the two in the middle, if the one on the top originally came from the chlorine on the left and the one on the bottom came from the chlorine on the right, now they've got 8 each because they're sharing. So there's another way to represent your covalent bond. An unshared pair or a lone pair is a non-bonding pair of electrons in the valence shell of an atom. So that'd be like these guys. These guys are not bonded, right? They're not paired. It's these guys that matter. One of them came from one of these atoms and the other came from the other atom. Oh, is this going to do this thing again? Okay. So what is a covalent bond in which two atoms share one pair of electrons? Caitlin. Yes, you're going to have your single bond there. It's going to do this thing. Yep. So the electrons can pair in any order. However, any unpaired electrons are usually filled in to show, bless you, how they will form a covalent bond. All right. So here's an example. You have H, hydrogen. He has 1 valence electron. And we said chlorine has how many?
1.
How many valence electrons? 7. How many do we want? 8 makes us happy. So when hydrogen bonds to chlorine, what is HCl? Does anybody know what it is? Yeah, but it's usually we see it as hydrochloric acid. HCl is usually we see hydrochloric acid written that way. And this is how you draw that type of bond with this nice little straight line. There are different rules for how you bond, how you draw that when you're drawing out the model. That's how, yes. Not quite this, no. So here's a sample problem. Draw the Lewis dot structure for CH3I. So if you've got paper in front of you, take a second and see if you can do it. CH3I. Everybody's like, what? So draw each atom's Lewis dot structure, count the total number of valence electrons. That's your first step. So what you should get is something that looks kind of like this. There's your C. Carbon has 4, right? H each has 1. Iodine is over here. Halogen. So he has 7. So you've got a total number of 14 dots. So then you want to arrange it so that the carbon is at the middle. So here's the part. This is where you can figure it out. See if you can figure it out. Your carbon is at the middle. And then you have 3 hydrogens and 1 iodine. So how are they going to work? How is that going to line up? 3
H's on each side.
Yeah.
The 1.
Yeah, there you go. So, guys. So you should have something it's going to be kind of like so. And you would have 2 dots, 2 dots, 2 dots, and 2 dots, right? And then you would have the remaining, right? Your remaining, the iodine would have the remaining 6 around the outside. All right, so let's look over your answers from your notes. How does a covalent bond form between two atoms? All right, Yusuf, what you got?
Covalent bond forms when two atoms share electrons.
A covalent bond forms when two or more valence electrons are attracted by positively charged nuclei of two atoms, thus are shared. Yes, shared between two atoms. What have you got, clay, or is that eraser stuff? Buddy, yeah. It's always good. I focus better when my hands are occupied. Make sure everybody has that answer, right? Everybody have that answer? Okay, number 2. Why is the H2 molecule more stable than two separate hydrogens? Jordan.
Like helium has a full shell.
Right, okay, there you go. So the H2 molecule is stable because each hydrogen atom now has a shared pair of electrons and has achieved a stable noble gas configuration. Molecules are stable when they achieve a noble gas configuration of an outer shell of 8 if they can, right? That's what you're aiming for. Or in this case, 2, because your noble gas on this side this is the only one that's not 8, right? This guy is 2, all the others are 8. He only has 2. So basically it's turned it into helium. And so I'm in a couple of Facebook groups for science teachers, and I'm in one that I actually screen captured it and posted it to my profile because I was blown away. But the question was, I'm going to read it exactly like it was written because I was dumbfounded. Or no, I forwarded it. I didn't screen capture it. It said something. No, I have to read it. Hold on. I have to read it because y'all are going to be like, huh? I mean, I was surprised that someone would post this in a group for science teachers. The question was, why? I'm going to read it exactly as they wrote it. Why hydrogen gas is not filled in balloons? I mean, it floats, right? Like helium. Why hydrogen gas is not filled in balloons? Why is it not? Why, Andrew? Yeah. Can we say Hindenburg? Like, hello, hello. And then everybody's like, because it's real reactive and it can explode and catch fire. And why would you do that? Why hydrogen gas is not filled in balloons? That's how it was written. Not why is hydrogen gas or why isn't hydrogen gas, but no, why hydrogen gas is not filled in balloons. All right, explain why the stability described in item 2, that would be this, does or does not hold true for most covalent bonds. All right. Okay, so molecules are stable when they achieve noble gas configuration with an outer shell of 8 electrons. Hydrogen is the exception because it achieves noble gas configuration when it has 2 electrons here. We just talked about that. This guy has 2, everybody else has 8. He's the only one that has 2, but he's nice and stable. Why is he stable with 2? Why?
Like helium, it has the 2 for the first shell.
There you go. It has to do with shells. Your first shell has how many electrons in it? 2 in your first shell. Your second shell has how many? 8. And because he has 2, his shell is full. It's about having a full shell more than having 8. All the others have 8 because that happens to be a full shell, but in his case, 2 is the full shell, so he can't interact with anybody. How does a covalent bond differ from an ionic bond? Okay, Gabe, what you got? There you go. Covalent bonds, atoms share 1 or more pairs. In an ionic bond, an atom transfers electrons to another. What is a molecular orbital? Oh, this is a good question. Who's got this? Caitlin, you have it?
A molecular orbital is the region of high probability that is occupied by an individual electron as it travels with a wave-like motion.
Yes. So it's about orbitals overlapping. So a region in which there's high probability that an individual electron exists as it travels in a wave-like motion in a 3-dimensional space around one or of 2 or more associated nuclei. Right. All right. Describe the potential energy change that occurs when 2 hydrogen atoms approach each other and form a covalent bond. Lucas? the energy decreases. Okay. Two atoms form a covalent bond at a distance where attractive and repulsive forces balance. At this point, potential energy is at its minimum. What is it called when two hydrogen atoms come together under a lot of heat and pressure? Do you know what we call that? Do you know?
Hydrogen fusion?
Yeah, where does that happen? Stars. Yep, in our sun, right? The sun is, yeah, you get fusion, you get nuclear fusion. That's all the sun is doing. Well, it's doing a lot, but that's what it's doing. You've got hydrogen atoms coming together to form helium atoms, and then those helium atoms are splitting apart, which is called what? Fission. So it's fusion, fission, fusion, fission all day long. That's what the sun's doing. That's where we're getting all the energy from, is from that fusion. I mean, fission. Anyway, in terms of energy, why is this hydrogen bond stable? Why is it stable? Okay, Yusuf?
Due to potential energy, when two hydrogen atoms come together to form a molecule.
So they end up having an electron configuration like helium, basically. You get two in your outer shell, and that is stable because that shell only has two. Your first shell only has two. So now you've got basically your noble gas configuration, and you're all good. Why is bond length an average rather than a fixed number, Jordan?
It fluctuates.
Okay, yes, because potential energy is going to determine that bond length, and yeah, it will fluctuate based on potential energy. Okay, describe the typical physical properties of substances that have metallic, ionic, and covalent bonds. Okay, somebody give me metallic. What are our physical properties of metallic bonds? Jordan. I mean, Asher. Keep doing that because you guys sit like here and there. Asher. Yep. Yep. They're also ductile and good conductors of and thermal energy. Okay, somebody give me ionic. What are Drew? There's one. Okay. How about, are they flexible?
No, brittle.
They're brittle. How about conductivity?
Well,
Not unless
water.
they're dissolved in solution.
Or
Excellent.
melted.
All right, and then covalent. Who wants to give me covalent? Caitlin?
Even if yellow gas, not a good conductor.
Covalent bonds. It can be solid, liquid, or gas. You're right. Not good conductors. Very good. So we got ionic bonds between anions and cations. They're caused by the transfer of electrons between atoms, usually a metal and a non-metal. And then our physical properties would be everything you just listed. Covalent bonds are bonds between atoms that share valence electrons, usually two non-metals. Metallic bonding is an attraction between metals with delocalized electrons. So it's not like a real bond, it's a little different. And then hydrogen bonds are the attraction that occurs between hydrogen atoms in a compound and strongly electronegative atoms with lone pairs of electrons, like oxygen, nitrogen. And that's not like a real bond either. These are more like real bonds, your ionic and covalent. So we're going to fill in these blanks. All right, Addie, what's my first one? Length. Bond length is defined by the average distance between two bonded atoms at their minimum potential energy. Who's got 10 for me? Gabe. Wait, Shanice did that one. Oh, I meant 11. I'm sorry. I meant 11. Energy. Okay, bond energy is defined as the energy required to break the chemical bond between atoms and separate them. Number 12. PJ. The tendency of an atom to attract bonding electrons to itself when it bonds with another atom is called its electronegativity. What kind of bond is the attraction between two atoms in which bonding electrons are shared equally between atoms? Colin. There you go. Non-polar covalent. And then a bond is what bond is an attraction between two atoms in which bonding electrons are localized on the more electronegative atom? I cannot speak. Gabe. There you go. Your polar covalent bond. All right. What's a molecule that has a molecule is one that a blank molecule is one that has a partial positive charge at one end and a partial negative? Addie? There's your dipole. Okay. In general, if the difference in electronegativity between two atoms is between 0 and 0.5, the bond formed is what kind? Xander. There you go. Yep, nonpolar covalent. And look, here's a little chart that shows you where the numbers go. If the electronegativity difference between two atoms is 0.5 and 2.1, the bond formed is, Addie? There you go, polar covalent. And if the electronegativity difference between two atoms is greater than 2.1, who hasn't answered me? Ooh. I've only got one in there for James and one in there for Liam and one in there for Colin. Which one of you wants this one? 18. Nobody wants it? The electronegativity difference between two atoms is greater than 2.1. It's right here. The bond formed. All right, take it, Lucas. They're both like, no, three of them. We don't want to answer. Okay, predict the type of bond that is present between sodium and fluorine in sodium fluoride, which is used in the fluoridation of drinking water. What do you think we have here? Gabe.
Ion.
There we go. It's an ionic bond. Very good. All right. Predict the type of bond present between carbon and hydrogen in polyethylene. Sure. You're not sure. You're changing your mind. James, is that a hand? There you go. It's a non-polar covalent. There we go. Predict the type of bond present between carbon and sulfur in vulcanized rubber. Oh, that's a fun one. Abby, I'll go with you again. Yeah, it's not a non-polar. This one's going to be non-polar covalent. Predict the type of bond present between carbon and fluorine in the polymer Teflon. Teflon. All right, Yusuf.
Non-polar covalent.
It's polar. All right. And predict the type of bond that is present between phosphorus and oxygen in a DNA molecule, Caitlin. Polar covalent. Okay, there we go. Y'all are so funny. All right, drawing and naming molecules. Oh, are we having fun yet? All right, an electron in the outermost energy level of an atom that can participate in bonding. What do we call these? Everybody together now?
Valence.
Thank you. A structure in which atomic symbols represent nuclei and inner shell electrons, and in which dots are used to represent valence electrons is Asher?
The Lewis structure.
There you go. Oh, click the button. There you go. Possible Lewis structure of a molecule for which more than one Lewis structure is written. What do we call this one? Caitlin?
Resonance.
There you go. Resonance structure. A covalent bond in which two atoms share two pairs of electrons is called, Xander. You go, a double bond. A covalent bond in which two atoms share three pairs of electrons is called, Lucas? A triple bond. All right. A bond in which two atoms share one pair of electrons is called, Asher? A single bond. Oh, you guys got those questions. Yay. A non-bonding pair of electrons in the valence shell of an atom is called what, Addie? There you go, your unshared pair. All right, methanol, which is CH3OH, can be used as a solvent, as antifreeze, it's not actual ethylene, and ethylene glycol. Ethylene glycol is antifreeze. And in the production of formaldehyde. Draw the Lewis dot structure. Okay, I'm going to show you the Lewis dot structure. I'm going to make it bigger so you can actually see it. This is what you should have, something like this for methanol. Check what you got and make sure that you're making sense of it. And there's your 8. You see your 8. Give everybody a minute to make sure you've got it. All right, propane, stuff you use in your gas grill. I'm going to draw the structure for propane, and it should look something like, oh, where did it go? Oh, no. Oh, no. Did I click it and it didn't show up? Hold on. Oh no. Where was I? This one? Oh, it came on. Oh, there it is. I was like, where did it go? I know it's here. There it is. So you should have something that looks kind of like that. Similar. You can have dots instead of lines, but yes. Okay, now draw the, I can't see it. Draw the Lewis structure. Oh, for water. That one's easy. Oh, come on. Should look like that. Everybody have something like that?
Easy.
Easy? How about carbon monoxide?
Easy.
That should look about like that. Now, what do these three lines mean? Triple bond, right? Triple bond. And how about the Lewis structure for the rocket propellant nitrile fluoride, NO2F? That's going to look like that. What this means is that this can be turned either way. Okay, when you get into organic chemistry, you'll learn that there are left-handed and right-handed molecules, like some are specifically positioned when they relate to others a certain way. And the ones that are flipped, they call isomers. So this was an interesting thing. The most recent time an isomer was like in the news. Okay, do you remember back during the COVID insanity when people were wanting to take ivermectin, which is a medication for like horses and livestock? Do you remember that? Okay, there was a while where people were like, ivermectin will cure your COVID. And people are like, why are you taking veterinary medicine? That's for horses. You can't take ivermectin. Well, then they came out with a new medication they started marketing. Does everybody remember Paxlovid? Yay, let's take the Paxlovid. It'll cure. It's essentially an isomer of ivermectin. It's the same thing. So all the people that were taking the ivermectin that people look at like they were completely crazy, maybe weren't quite so crazy because what they ended up marketing was nearly identical, but they gave it a new name and they told us all. They told us all, but chemically speaking, they were extraordinarily similar. All right, so how about the Lewis dot structure for this little molecule? Sulfate with a 2 negative. That one's a little funky. Anybody get that or close to it? Something like that. Maybe you could have the O on the bottom. Flip the other one. You know, you could have it on the bottom as opposed to on the top. All right, what's the difference between single, double, and triple bonds? That's real easy. That's the fact that you got 2 atoms share 1 pair of electrons in single, 2 atoms share 2 pairs of electrons in a double, and 2 atoms share 3 pairs of electrons in a triple. All right. What does VSEPR theory predict? Jordan.
The shapes of molecules.
Yes.
Based on the balance.
Yes, the shapes of the molecules, the general shape of a molecule. You paying attention in the back? So if you were to draw the VSEPR theory, use the VSEPR theory to draw these molecules, I'm going to show you what they should look like. That's what you're looking at. Anybody even take a stab at it? That's like, whoa, right? So here's your methane, your CH4. Remember earlier I was like, CH4 is your methane. Carbon tetrachloride and dinitrogen oxide. Oh, sorry, nitrogen dioxide. There's your laughing gas, right? All right, so how does one unbonded pair of electrons affect the shape of a molecule? Lucas? Yeah, electrons, yes, they're going to repel. So that's why you get these ones that are so far away, right? Some of them, that's why you get the bent. And that's why you get them spreading out because they're repelling each other. How do multiple unbonded pairs of electrons affect the shape of a molecule? Gabe? Yeah, they repel each other and they cause it to be bent. Very good. What evidence is there to support the idea that opposite polar ends of molecules attract each other. What you got, Yusuf? Yeah, that's one way. So the energy required to separate polar molecules is greater than what's needed to separate non-polar. If it's non-polar and everybody's sharing the electrons equally, then it's good. It's easier to break apart. But the polar ones are much more difficult to break apart because one of them is holding onto the electrons much more strongly than the other. How do polarity and shape of molecules relate to the properties of a substance? What you get? That's a good answer. So shape and polarity can affect the way a molecule fits into another structure, how it tastes, as well as the ease of separation and attraction to positive and negative charged objects. Lots going on. All right. Here's your inorganic nomenclature flow chart. This is what we did the other day. It looked a little different, but it was the same thing where you follow these steps. Okay, on your exam, on your test, you will be asked to name some compounds and you will be asked to take the compound name and come up with the formula. There will be a periodic table in the resources for the test, and there will be a naming flow chart in the resources for the test. So you'll have a nomenclature flow chart, you'll have a periodic table. They're both there for you to use. I want you to use them as tools because we're just getting introduced to this naming. Now, by the time you get to midterms, there are some that I expect you to recognize. If I ask you what HCl is, I expect you to come back with hydrochloric acid is most likely what you're talking about. If I asked you what KCl is, potassium chloride, some of them I want you to recognize, CH4, because they're things that you're going to use and they're going to be common. All right, so here we're going to name some. What's this one? What's the PbCl2? Colin. There you go. Lead 2 chloride. This goes back to that charge, remember? KCl, I just said it a second ago. Gabe? There you go. Potassium chloride. LiO2. Jordan?
Lithium dioxide.
Lithium oxide. And that's because of how, technically dioxide, but yeah. This is one of those ones that we kind of, meh. How about this one? AS2O3. Caitlin.
Arsenic trioxide.
Arsenic trioxide. Oh, that's fun. How about PBr3? PBr3. PJ.
Phosphorus tribromide.
Phosphorus tribromide. SF4. Yusuf.
Sulfur tetrafluoride.
Sulfur tetrafluoride. N2O5. Caitlin.
Nitrogen pentaoxide.
Dinitrogen pentoxide. Very good. All right. Now, nitrogen monoxide is what? Gabe?
No.
Yeah, no. Yep, pretty much.
No.
Carbon dioxide is everybody. Yes, carbon tetrachloride is going to be Jordan?
CCl4.
CCl4. Very good. And carbon disulfide, Gabe? CS2. Very good. And those this one and this one should have been subscript, and I don't know what happened to them. Okay, now, hold on. In case you missed it over the weekend, did anybody miss this? Because this was insane. Okay, SpaceX did the unimaginable. They launched their Falcon Heavy. They separated the rocket boosters. Usually they bring that booster down Marvin the Martian style. It's an old reference, but that's how he landed his little ship on the moon. But they bring it down and they stick it in the ocean on one of those little landing pads, right? This time they returned it to the tower and they got it right on their first try. Their trials beforehand, they were within 2 centimeters of error. This thing is like, what is it, like a 40-story building? Something like that. And they were within 2 centimeters, which is insane. But watch this. If you didn't, this is not being played in reverse, which is what it looks like. This is being played forward.
Stolen.
Oh, not this again. I'm gonna lose it. I need to figure out how to make it go away. All right, here we go. From space to this. SpaceX. They call those the chopsticks.
For the first time ever, the booster returned back to the launch site where it was caught by a mechanical chopstick. Well, there were mechanical chopstick magnets actually. As critical to its goal of making that rocket fully reusable.
So it's a reusable rocket, but here's the crazy thing. Thanks for Al Roker. So here's the thing. Why do they want it to come right back there? Drew?
Because it hurts the landing gears, the longer you keep it there, and it's cheaper.
That's true. And why are they bringing it right back to the launch pad as opposed to sticking it out in the ocean? What are they trying to do? Do you know? Do you know? Recover it, but they can recover it from the ocean. Do you know?
They're trying to reuse it.
They're trying to make, you can still reuse it from the ocean. They're trying to make the reusability within hours. That's insanity, y'all. Like that's it. If you ever saw the way they moved the space shuttle to the launch pad, it was on this thing called a crawler and it moved like super slow and it took days to like get there. Yeah, basically it was.
Burning a lot of fuel, sending a boat out to go get it.
That too, but nowhere near as much as that rocket's burning. All right, here's what is on your test. You have your test tonight. Oh my gosh, wait a minute. We just had a test sometime this week. It's available now, tonight, whenever you want to take it. You will need to know for your test, Lewis dot symbols, covalent versus ionic bonding, bonds and electronegativity, characteristics of covalent and ionic bonds, naming compounds, writing formulas from compound names, and then naming compounds based on the formula, right? Polar covalent versus non-polar covalent, cations versus anions, naming ions, naming ionic compounds, and predicting the behavior of elements of ions based on their location on the periodic table. And you will have access to a periodic table and a compound naming flow chart this time around. Question. That is entirely up to your parents. I prefer you don't open book them, but they're the ones giving you the high school credit. So they're the ones that get to decide what you can and can't do when you're testing, which is why you do it at home and not here. So here's the thing though, your midterm's not open book and you'll need to know this stuff when your midterm rolls around. All right. No. No way, son. It ain't happening. All right. So have a good week. I'll move the money over here.
What did our parents say the midterm is open book?
Yeah, that's too bad because you do that part. You do that right. Yeah. No, that was a mistake. It shouldn't have been in there like that. Yes.
Do you notice anything with my outfit?
What?
You wearing mushrooms? And I saw that one earlier. This one's adorable. I love it.
But
Very
I was
cute.
waiting for, I'm not gonna booth. So I cleared to do. Start reading out of the booth.
Yeah, your mom said that you wear it as little as possible or something, I think is what it said. That
And
is
then,
great.
Before Halloween, I cleared out of the booth.
That is fabulous news. Are you super excited about that?
I'm so excited. I hate wearing it.
I bet you are. I would be tired of it too.
It's so annoying.
Yeah, it is. They're annoying and they're at least you can take it off